In this video, we're going to go over how to write Arrhenius modified reactions for monoprotic and polyprotic acids and bases. So what a monoprotic acid is an acid that only has one hydrogen to give up to water. Okay, so just kind of breaking down this word here, mono, that just means one. Whereas protic sounds kind of like proton, which is what our H plus ion is. So that's how you can remember what monoprotic means. And acid, remember A for away. The hydrogen is going to go away from the acid. So some examples of monoprotic acids would be hydrobromic acid, hydrochloric acid, hydroiodic acid, hydrofluoric acid, so on and so forth, right? Because all of these only have one hydrogen to give up to water. So the number of times an acid can react with water is usually going to be equal to the number of hydrogens that's at the front of the formula. So that's helpful to know when you're writing these modified Arrhenius reactions here. So, for example here, if we have hydrobromic acid, and we're reacting it with water because we're writing a modified Arrhenius reaction. So hydrobromic acid, if we look that up, we can find it right here. So it's one of our strong acids because it's above the gray hydronium line. So that means I use a single-headed arrow. Okay, so acids, remember A for away. The H plus, or the proton, is going away from the acid. So this is our acid here. Okay, so now what we'll have is our hydronium ion. So hydronium is always going to be aqueous. It's never going to be liquid. Okay, liquid is for water, but not the hydronium ion. Okay, and then if we imagine HBr just with one less proton, then it's just going to be a bromide ion. And there you have it. With polyprotic acids, the word poly just means many. So what this means is two or more hydrogens that it can give up. So two or more. So protic, that just means our proton, our H plus ion. Acid. So acid tells us that the proton is going A for away. Okay, so polyprotic acid has two or more hydrogens to give up to water. And this means that they can react with water more than once to produce multiple hydronium ions. So again, going back to this statement up here, the amount of times you have to write reactions, or how many reactions you need to write, for acids, it's going to be related to how many hydrogens you have at the front of the formula. Okay. So for a diprotic acid, so di just means two. So this is saying that we're going to deal with an acid that has two protons to give A for away to water. That's what this means. So two protons, or H plus. Okay. So, for example, let's say we have H2SO3 aqueous. So, that is sulfurous acid, and where we're going to find sulfurous acid is right here. Okay? So, since it's below the gray hydronium line, this means that sulfurous acid is a weak acid. So that means that we need to use our double-headed arrows. So plus water, double-headed arrows because we're dealing with a weak acid. And again, we're only going to move one proton at a time. Okay, so we're going to produce our hydronium ion because that's water with one extra one extra proton. Plus, now we just got to kind of imagine our acid with one less proton on it. So that's going to be HSO3. And for the charge, since it was neutral here and it lost a 1+ charge, that means that the charge on hydrogen sulfite is going to be 1-. So aqueous, here we go. Okay, however, since this is a diprotic acid, what we're going to want to do is we're going to want to keep on reacting in this case it's the anion here. So how you choose which ion to keep on reacting is, well, it's not going to be hydronium because that's what gets produced when an acid reacts with water, and we want to keep on reacting the acid with water to show what happens. Okay, so that's why I'm saying let's choose hydrogen sulfite and keep on reacting it with water. So I'm going to write HSO3 aqueous with the 1- charge plus water, and this is still going to be a weak acid. Where you can find that is, let's see, HSO3 you're going to find right there. So it's between the two gray lines, so the hydronium ion gray line and the water gray line. So that means it's still a weak acid, and that's why I'm going to use double-headed arrows still. Okay, so we're moving one hydrogen at a time. Do not move more than one proton or one H+ ion at a time. So H3O+ aqueous plus. So the hydronium ion is just water with one extra proton on it. Now we got to visualize this with one less proton on it. So that's going to look like SO3 2-. Why the 2- charge? Well, we started out with a -1 charge and we lost a 1+ charge, so if we lost it, gives us -2. And since we have no more hydrogens to give away, that is our clue that we are done. Okay, so I'm just going to write out what I was saying about the arrows just above here now that I'm done this example. So just as a reminder, use the double-headed arrows if we have, or if we are reacting. A weak acid or weak base. So that's going to be really important there. Okay, triprotic acid, breaking this down, that means we got 3 protic proton, so we got 3 H+ ions to give away. So, for example, we're going to have to squish this in here. Okay, so let's say we have phosphoric acid. Okay, so phosphoric acid, we'll be able to find that right here. So it's a weak acid, So that means we got to use the double-headed arrows. So reacts with water, because we're doing Arrhenius modified reaction. And we are, once again, only moving one proton at a time. So we are going to get hydronium, which is going to be aqueous. It is not going to be liquid. Plus, now we got to imagine our acid with just one less hydrogen. So H2PO4, and it's going to have a 1 minus charge. Why? Because it started out neutral and then we lost a 1 plus charge, so that's why it's 1 negative. Okay. And another thing to watch out for, always write out your states there. One other thing to watch out for, water is always going to be liquid in these reactions. Water is never aqueous. Okay, that's a common mistake that I see. All right, so for the next reaction here, we're taking our anion and we're going to continue to react it as an acid. So H2PO4, aqueous, 1 minus, plus water. All right. And then we're giving away a hydrogen, or a proton, sorry, because it is an acid and acids give away their protons. Okay, so we have our hydronium ion plus HPO4, 2 minus. And then we're going to keep on reacting our anion. So HPO4, 2 minus, aqueous. I'm actually going to move that a little bit higher up. Plus water. And we are going to get hydronium plus PO4, 3 minus. I guess I should keep this consistent and put the negative in front. And there you have it. So you don't always have to write this like this, what I have in blue here with moving the H plus over, but I do find it's helpful for students to kind of help them figure out what their products are going to be here. Okay, so if it really does help you, absolutely you can write it. All right, and that is completely done because we have no more hydrogens left to give away. For bases, so remember bases, you're running towards home base in baseball, so bases accept hydrogens. Or another way to look at it is that your protons are going to go towards the base. So for bases, generally the number of times an ion can act as a base, so what that means is the number of times a base can accept a proton, or H plus ion, is going to be equal to the negative charge on the ion. So if your base has a -1 charge, it can accept 1 proton. If your base has a -2 charge, then it can accept 2 protons, so on and so forth. Okay, there are exceptions to this, the one being ammonia. That one, it has a neutral charge, but it can still accept hydrogen there. So let's write that as an exception. So ammonia, this is a monoprotic base. So what that means, mono means 1, protic means proton, base means it accepts the hydrogen. Okay, so ammonia acting as a monoprotic base here. So what we can do, and sometimes, like, you can write water as H2O, but it might be a little bit helpful to write it as this. HOH is the exact same thing as H2O. Why? Because we still have 2 hydrogens and 1 oxygen. Okay, it's just written a little bit differently, and the reason why I'm writing like this is so that it's a little bit easier to see what I'm going to do here. Okay, so the hydrogen goes towards the base. So then what we get is hydroxide, because we're imagining water with 1 less proton, plus NH4, 1 plus, aqueous. Okay, so ammonia, that's a monoprotic base, which just means that it can accept 1 proton. Alright, with sodium hydroxide, that is also another monoprotic base. However, because it's an ionic compound, first we have to dissociate it, and then we can react it there. Okay, so the dissociation equation is going to be our metal cation plus our hydroxide ion. Okay, and then you always pick the anion to react with water. Alright, so I'm going to have to continue this over here. Okay, so with our anion, reacting it with water, which I'm going to write as HOH. Again, if this bothers you, just write it as H2O. Okay, and since hydroxide is a strong base, I'm going to rate it as a single-headed reaction arrow. The reason why I put this as a single-headed reaction arrow is because dissociation equations always have a single-headed reaction arrow. Okay, and so what's happening here? We have our 1 proton move over. So water with 1 less proton is just going to give us hydroxide, plus hydroxide with 1 extra proton is just water. So you can write water as H2O or HOH, however you prefer. Okay. So for a polyprotic base, breaking this down, poly just means more than 2. Protic means H plus, base means that it accepts it. So what this is saying is that a polyprotic base is a substance that can accept more than 2 protons. Okay, so what this means is that they can react with water more than once to produce multiple hydroxide ions. So with a diprotic base, what that means is it's going to accept 2 H plus ions, or 2 protons. So for example, let's say we have sulfate ions, so that's SO4 2 minus, aqueous. So the 2 minus, that tells us that this can accept 2 hydrogens. Plus water. And sulfate ions, since it's not hydroxide, it's a weak base, so that's why I'm using double-headed arrows. You can find it in your data booklet, and where we would find sulfate ions is right here on page 8. So I'll zoom out a little bit so you can see, just right there. Alright, and then we are just transferring 1 proton at a time. So we're going to get hydroxide ion plus, so that's just the water with one less proton. And then now we have to imagine our sulfate ion with one more proton on it. Okay, so that's going to give us HSO4, 1 minus. The reason why the charge is 1 minus is because we started out with -2, and then we added a 1 plus charge, so that's going to be -1. Alright, so now what we're going to do here, so hydroxide is what we're aiming to produce. Okay, I know that I said, okay, you always pick the anion to react with water, but now we have two anions. Okay, so you're not going to be picking hydroxide. You're going to be picking the other anion that is not hydroxide to keep on reacting. Okay, so that's why I'm going to start with HSO4, 1 minus, aqueous, and then we're just going to keep on reacting it with water here. So it's still a weak base. So double-headed arrow. We're only transferring one hydrogen. We produce hydroxide, and then this with one extra proton is going to give us H2SO4 aqueous. And now it has a neutral charge because we started out with -1 and we added a proton, so that's why it's a neutral charge. Alright, triprotic base. So what this means, so base means that it's going to accept. Tri means 3, proton, or protic means H plus ions. Okay, so a triprotic base will accept 3 hydrogen ions, or 3 H pluses. Okay, so for example, if we have our borate ion, so BO3, 3 minus, aqueous, plus water. So borate ions, where we are going to find that, well, actually, we're not going to find it on our, or in our data booklet. However, we can assume, since there's no hydroxide in it, that it is a weak base. So that's why I can still write the double-headed arrows. And once again, we are only transferring one proton at a time. So then we have our hydroxide ion plus HBO3, and now our charge is going to be 2 minus. Now we're going to take this anion and keep on reacting it. So plus water, it's still a weak base because we still don't have hydroxide in here. So we're still going to produce hydroxide ions, and hydroxide ions are what make bases basic, or a basic solution, is their ability to produce hydroxide ions. So now this with one extra proton, that is going to be H2, BO3, 1 minus. You could either write 1 minus like this or just like this. Either or is fine. And we're going to take this and react it once again. The reason how I know to keep on reacting it is because for bases, you typically go until you have a neutral charge. The only exception to that would be ammonia. You go until you have a 1 plus charge. So plus water, still transferring, only one proton. So weak base, so double-headed arrows, produces hydroxide plus H3O, BO3, aqueous, and now it has a neutral charge, and that's your clue that you're done. Okay, so just as a heads up, I like to write either hydroxide or hydronium, kind of depending on if I'm working with an acid or a base. I like to write that as my first product, just to get it out of the way. However, does the order matter in which you write your products? No. You could have written your hydroxide ion second instead of first on your product side, and it would have been fine. Okay, so you can write this equation. So I'm just rewriting this same equation. I'm not changing anything, just to show you. You could have written this equation like so. And that's still correct. Okay, so long as you have the correct reactants and the correct products, as well as you're using the correct arrows, you're good. Okay, but it's up to you. I just like to write either my hydroxide ion or my hydronium ion first, just simply to get it out of the way. That is the only reason.